back to the illumination talks, and today we're going to talk about the Carolina Bay impact theory. Different topic, just for a change, why not? Let's look at something a little bit different. So you're going to ask, what is a Carolina Bay? Well, this is a Carolina Bay. In fact, this is several of them. This is an aerial image, obviously, taken by LiDAR, which is laser detection and ranging system, which gives you the height above the ground. So effectively, it's giving you contours. It's highlighting the topography of the ground. And you can see in this little section of, well, this is in Carolina, of course, and you can see a number of what are known as bays. They're like ponds, but they're not always associated with ponds or water. They're just depressions in the ground, often in alluvium deposits, so silts and sands, quite often in coastal regions and around sort of river deltas. So they form quite easily in soft silts and sands. And it's just a depression in the ground with a rim of sand or silts all the way around the edge. And these can range from a few tens of meters, I suppose, up to 10 kilometers. So some of these bays can be very, very large. There's significant features in the landscape, and they would take a lot of energy to make these formations in the ground. And as you can see, they are pretty much perfect ellipses. They're very symmetric, almost man-made looking. One of the persons who's been investigating these bays says they are cookie cutter perfect. They look as though they're man-made. And they're not simply just symmetric and elliptical. They're directionally orientated as well. You can see they're all sort of pointing in the same direction. So whatever forces have made these bays is consistent in this region. It's forming all of the bays, no matter what their size, in a similar shape and a similar orientation, which is interesting. And this is what they look like in a normal aerial photo. So this is not LiDAR, of course. This is a normal photo. And okay, they don't show up so well, but you can still see them in the landscape because they've changed the vegetation and the drainage of the land, and so you can see them in the landscape. And obviously we have a lot of man-made features that have been built on top of them, but these bays have been here obviously for thousands of years. And they're known as Carolina Bays, but they're not just in Carolina. They're up and down the east coast of America, all the way down to, there's one or two even in Texas. And they're also in central North America as well. So here are some Carolina Bays in Kansas and Nebraska. And you can see they are the same type of formation, except that they're pointing in the opposite direction, and we'll come on to why that should be later, because that's a little bit of a mystery. That is why they should be pointing, consistently pointing in the opposite direction. So there are two main theories, I suppose, as to how these Carolina Bays have been formed, because there is no established theory as to how these Carolina Bays have been made. It's very much open to debate, and the two main theories that have been put forward are the Aeolian theory, which is wind formation, so a gradual formation, maybe over hundreds, maybe thousands of years, to create these Carolina Bays by wind erosion, deposition of sands and silts to form the rim of the bay. Or the other one, slightly more dramatic, is the impact theory, that these are actually craters, because they do look like craters, impact craters, from some body that's some projectile that's come into and struck the ground and created this Carolina Bay almost in an instant. And this talk will be looking at evidence for the impact theory, that these are extraterrestrial impacts, possibly created at the beginning of the Younger Dryas cool period, and we'll go into that later in this talk. But that's a favourite era for looking at this impact theory, because there was a change in the climate at that particular point. And this impact theory is, well, it's not a new theory, certainly not my theory, that's for sure. The first mention I could see of it was from Melton and Shriver, which is from the 1930s, and they proposed that these bays were caused by meteor impacts. And then we had Eaton and Parkhurst, who made a very interesting science paper on these bays back in the 1970s. More recently, we've had Weston Firestone, and they wrote a book, and they wrote two papers, I think it was, back in 2005 and 2007. And they came up with a lot of extra information, which is very interesting. Would recommend reading their papers. And then more recently, we've had Michael Devias, who's a geologist, and he's created a website dedicated to the Carolina Bays, which is called syntos.org. And that has a lot of information on the possible formation of these bays and lots of images of the bays themselves as well. So it's a great resource if you're interested in looking at the topography of these enigmatic, I suppose you would call them, Carolina Bays. So we have these two theories, the wind theory and the impact theory. And, well, let's look at both of them and see their merits and their problems. So, wind, first of all. So, what sort of problems do we have with this wind theory? Well, I suppose the first one is their symmetry and the elliptical shape. So this is that picture that we saw before, the LiDAR picture, I'm sorry. And as you can see, the bays themselves look almost man-made. They're almost perfect in their elliptical shape. And you have to ask yourself, would a wind-generated bay feature, this depression in the ground, which may have contained water, of course it may have been a pond in the past, although most of them are not at present, would this feature, would the wind have caused such a symmetrical feature on the ground? Well, we have other examples, or possible other examples, and we can see features like these, which are up in Canada, up near Greenland. And here we see sort of well, they're not quite elliptical, but they are certainly symmetrical, round features in the landscape. And they are ponds, of course, as well, as you can see. But these are not even aeolian. These are not wind-formed ponds. This is caused by permafrost thawing that has created these circular ponds. And of course, this mechanism wouldn't be available in Carolina. This is the thawing of permafrost that has caused these. So, no, these particular features are not the same as Carolina Bays at all. Another problem with these bays is they're highly directional. They have a very similar orientation within one population, within one region. They do change, as we will see, as you go from region to region, but within every particular region they have a particular orientation, as we've seen before. on this particular diagram. And, well, you can get directionally orientated ponds. You might call them bays, but they're not quite the same. And this is often given as an example of wind directional ponding. This is up in Alaska near Barrow, I think, in Alaska. And okay, these are directional ponds, but they're certainly not elliptical, and they are certainly not cookie cutter elliptical. They're just not the same as the Carolina Bay depressions. And we're not even actually sure if these are wind-formed at all, because ever since the sort of 1930s, these bays here, these ponds here, have been taken to be wind-formed because of the prevailing winds up in northern Alaska. But a recent paper said they were actually permafrost thawing ponds again. And so they were directional because they were orientated towards the sun, not because of the winds. So even with these directional ponds, we're still not sure if these are wind-formed or not. And of course, if they are permafrost-formed, melting of permafrost, then again, this mechanism does not apply to any bays down in Carolina. And then we have the continental orientation of the Carolina bays, because as we saw before, different populations of bays have a different orientation. So the Carolina bays in Carolina will point out towards the northwest, but the bays in Nebraska and Kansas will point out towards the northeast. Now, for this to be wind-formed, you would have to have a circulation pattern which was steady over North America that changed between the central states and the coastal states. Now that does not happen now, and no rational reason has been given for it actually happening in the past when these bays were thought to have been formed. So again, this continental orientation of the bays is unlikely to have been generated by wind circulation patterns. And the other problem, I suppose, with these bays is there are no other examples like this around the world. Which is odd. If these were just wind-blown features that have formed naturally from prevailing winds, then you would expect to find them in many locations, coastal locations, estuary locations with soft silts and sands that would form directionally orientated, symmetric, elliptical bays. But we don't find them around the world. The only one I found, and I found this just a few months ago, is these bays. And again, we see here elliptical bays, directionally orientated, and they just look like Carolina bays. Unfortunately, these are man-made. This is in southern Spain, and these are man-made. These were made for environmental reasons. Someone wanted to make some shallow ponds for the local wildlife, and they happened to make them elliptical and orientated without even knowing anything about the Carolina bays, because I did ask them why they had done this, and they just said it was just what they wanted to do. So these are actually man-made Carolina bays. So there were no other examples of these bays across the world. And that's odd if these were just natural wind-formed formations. So the wind hypothesis for the formation of Carolina bays is unsatisfactory, to say the least. But what about the impact theory? Well, Others have said that these are meteor impacts, which might sound reasonable. So you have a meteor shower, not just one meteor, but a meteor shower comes in from the northwest and lands across America, North America, and gives us these directionally orientated impact craters. But this type of theory has as many problems as it does advantages, and that's why I formed my own version of this, which is based on Michael Devias's idea of a large meteor striking the Laurentide ice sheet. So we're talking here about 14,000 years ago, when there was still an ice cap across North America, which came down all the way past the Great Lakes, and this was known as the Laurentide ice sheet. So the idea is that a large meteor, came in from the northeast, struck the Laurentide ice sheet, and blasted this ice, debris from this ice sheet, all over North America. And so you get these great ice blocks landing across America, making these Carolina bays. But I go a step further than that, because obviously this is a massive impact on a fragile ice sheet. And so the ice coming off, the debris coming off this ice sheet, would not be ice blocks, it would be crushed ice. And so what you would get is blobs of ice, slush balls you might call them, like snowballs, but denser. So let's call them slush balls, all flying off in different directions and impacting across North America. So that's the basic theory, and it gives us some problems, but it gives us many advantages over the aeolian or wind-formed theory. So let's look at some of those advantages and disadvantages as well. So for the impact theory then, one of the advantages is it would explain the symmetry of these craters, the cookie cutter perfect shapes, because craters do form cookie cutter perfect shapes. But you might say, looking around the moon and Mars and various other bodies around the world, that all impact craters are circular. But that's not entirely true, because as this graph by Professor Elbenhausen demonstrates, the shallower the impact, the more elliptical the crater. So if you look on the bottom left, you will see that below 10 degrees, the impact trajectory of the projectile, below 10 degrees, the crater starts to become elliptical. And if you get below 5 degrees, it becomes very elliptical. And so you can get elliptical symmetric craters from an impact if it is a shallow impact. And of course, these may have been shallow impacts, because we're no longer talking about an impact coming out of the solar system, a meteorite impact coming at any old trajectory and hitting the ground. We're talking about a local projectile, so secondary projectiles that have come only from the Great Lakes, which is not very far away, of course, 1,000 kilometers, 1,500 kilometers. These are short-range projectiles that have come from just up the road, and they may well have a more shallow trajectory and therefore formed elliptical craters. And here is an elliptical crater. This is an image here of Melis Dorsa. This is on Mars, and it's up by Olympus Mons, which is the largest volcano in the solar system. And this is classed as an elliptical crater. It's not very elliptical. This must be the one that's formed from a a trajectory of about 10 degrees or so, because it's only partially elliptical. But this is an elliptical crater, and you can see the splatter pattern around it as well. And you can get the same effects if you just do a very, very simple experiment using sand balls and throwing them at a low angle onto the beach, and you'll get elliptical craters like this. I mean, it's a very simple experiment, but you do end up with elliptical craters. I did ask a university that had the correct equipment to investigate this, but they declined because they said, oh, no, the theory is impossible and therefore it's not worth our time investigating. So nobody has actually investigated what would happen if you had a slush ball hitting silts and sands at a low angle to see what sort of shape of crater that it would make. So that needs some further investigation, of course. Anyway, one of the other problems or merits of the impact theory is the local direction. So as we saw before, we'll have a look at this image again. Within each population, within each region, all of the Carolina bays line up and point in the same direction. Difficult to explain with wind, but of course, if all of these projectiles originated from the same location, then of course they would all point in the same direction because they're all pointing back to the origin of these projectiles, the same radiant. They would all point in the same direction. So this oddity of Carolina bays is easily explainable if these were secondary projectiles that had all come from the same position on the Laurentide ice sheet. And this would also explain the continent-wide orientations of these Carolina bays. So if we start in the north on the east coast, up sort of Virginia way, they point more to the west. And then as we come down the east coast, down through the Carolinas towards Texas, they start to turn more to the north. They become more northwesterly. So all of these populations have different orientations. And then if we go across to Nebraska and Kansas, the ones over there have completely different orientations because they're pointing out towards the northeast. Again, difficult to explain with wind patterns because you would have to have this circulatory wind pattern across America that stayed there for long periods of time and gave prevailing winds that would give these different orientations in different parts of North America. Doesn't happen today. There's no good reason why it would ever have happened in the past. However, as far as the impact theory goes, of course all of the bays will point in different directions because they are all pointing back to the origin on the Great Lakes, on the Laurentide ice sheet, which used to sit over the Great Lakes region. And this is a diagram from Michael Dryas, who's calculated all of the orientations of these particular bays. And they all seem to point in the same direction. Easily explainable by the secondary impact theory. It's probably worth pointing out actually that actually all of these orientations point towards the west of the Great Lakes, not at the Great Lakes. Why? Because of Coriolis. And Michael Dryas has very cleverly gone through all of these Carolina bays and corrected their angle for Coriolis and for impact slew when the actual projectile hit the ground. Coriolis, it's probably worth looking this up on Wiki because it's difficult to explain what this is without seeing lots of diagrams of how it works. But Coriolis is a force, well actually it's not a force, it's an apparent force caused by the rotation of the Earth. So all projectiles running across the Earth will appear to be curved to the right in the northern hemisphere. Now the projectile itself is not turning, it's going in a straight line, but because of the rotation of the Earth, it appears to turn to the right in the northern hemisphere and to the left in the southern hemisphere. This is what makes hurricanes all turn in the same direction. So a hurricane will always be anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere because of Coriolis force. And even coming back to something that's more like our slush ball projectiles, even an artillery shell will be deflected to the right in the northern hemisphere. And so here's a little image of our cannon firing in the northern hemisphere, and our projectile, we expect it to go straight ahead. But it doesn't, it turns to the right. And again, of course, the projectile is going in a straight line. It's the Earth that's turning underneath it, which makes it appear to go to the right in the northern hemisphere. Well, the projectiles coming out of the Great Lakes region will do exactly the same. They will apparently turn right as they fly across North America. And when they land, the bays, the craters that they form, will preserve that change in their orientation. And so to find the actual origin of these Carolina bays, you have to correct for Coriolis and for the drift angle of impact. And that's what Michael Dryas has done very cleverly. And that changes the orientation from pointing towards the west of the Great Lakes to pointing at the Great Lakes. Another point about the impact theory. So the bays are all shallow impacts. The Carolina bays are only, between 2 and 5 meters deep. I mean, they're very, very shallow impacts. Whereas craters, we know what meteorite craters look like. They look like this. This is meteor crater. And as you can see, it's a deep, deep impact caused by a huge projectile coming in at orbital speeds and hitting the Earth with some force and causing this enormous great crater. And of course, this looks nothing like the Carolina bays, which are shallow little ponds, only a few meters deep. Well, there is a difference, of course, because meteor crater was caused by a huge rock or iron meteorite coming in at orbital velocities. But the Carolina bays weren't caused by that same mechanism. These were secondary impacts. And so they were caused by slush balls coming in at lower speeds. These were suborbital projectiles, more like an intercontinental ballistic missile. And although fast, they're coming in at much slower speeds than a meteorite from outer space. And so when these slush balls touched down, they would deform. The slush ball would deform. The ground would be deformed as well, but the slush ball itself is not going to make a deep crater. It's going to splash down. It's not going to hit down on the surface. And it's going to form this shallow bay-like structure. Well, that's the theory. Again, it's not been tested. We did ask for some universities with the equipment to actually test this, but they declined to do so. Another problem that's levelled at the impact theory is the carbon dating. Because these bays have been investigated, of course, and bits of wood and so on have been taken out of the bay rims, and they have often been dated to up to 40,000 years ago, which is actually about as much as you can do with carbon dating, but there we go. And they've said up to 40,000 years ago. And that is a problem because the main period we're looking at for this impact is going to be about 12 or 13,000 years ago. And so these wood samples are far too old to be connected with the impact we're going to look at. But that's a bit of a nonsense, because the problem with carbon-14 dating, the primary problem with all carbon-14 dating, is the sample you're testing contemporary with the structure you're trying to date? So if you're trying to date a temple, for instance, and you found a piece of wood there, is that piece of wood contemporary with that temple? Or was it put there later? Or was it there before the temple was even built? You're not necessarily dating the structure where that piece of carbon or wood actually lies. And the same is true of the Carolina Bays. If you can imagine, there was a wood sample in the ground, in these sands and silts that had been sitting there, and it had been sitting there for 20,000 years, say. And then along comes this slush ball, impacts the ground, splash down, forms the bay, throws up all of these sands and silts into the rim of the bay, and that piece of wood is taken into the rim of the bay. So what is the date of that piece of wood? Well, it's not been changed. It's still the same old date. The carbon-14 date will still give the same date of 40,000 years ago. It's just been transferred from one location to another. So dating pieces of wood in the rim or even in the bay itself does not give us the date of the impact of this particular bay formation. It's the old problem, is the carbon-14 dating contemporaneous with the artifact you're trying to date? And so that can't be used to disprove the impact theory. Same goes for thermoluminescent dating as well, which is the other technique that geologists often use to date formations in the environment. Thermoluminescent dating is slightly more complex. So a piece of quartz can have its date reset by strong sunlight, especially, sometimes strong heat, but mainly by strong sunlight. And after that date, it starts to age. And you can date that age of that particular quartz sample. So after its date has been reset, 20,000 years goes by, you test it, and the thermoluminescent dating will say 20,000 years. So if you can imagine a large sand dune being formed, each grain of sand being laid down year by year, making this huge great sand dune, maybe 50, 100 meters tall. Each grain of sand will be reset as it's laid down on that sand dune. And then if you dig into that sand dune and take samples many thousands of years later, you will be able to date each grain of sand as you go down through the sand dune. And hopefully, if your dating system is correct, you will get a series of dates going from very old to very young throughout the whole of the dune. That's fine, that works. And so you can date the age of the dune. However, that doesn't work with Carolina Bays. So if you had had these grains of sand sitting there in the environment for thousands of years, because some of these thermoluminescent dates go back 120,000 years or more, so these grains of sand have been sitting there in the environment, minding their own business, covered up, and then comes along this huge great slush ball, slams into the ground, splash down, we get the formation of a Carolina Bay. Well, those grains of sand have not necessarily been reset. They're now sitting in the rim of the bay, and they're saying 120,000 years old. But that's not the date of the bay, that's the date they were laid down in the ground originally. So again, same problem as we saw with the carbon-14 dating. Is that date contemporaneous with the creation of the Carolina Bay? No, it's probably not. So we cannot use thermoluminescent dating to disprove the Carolina Bay impact theory. The other thing that's often levelled at the Carolina Bays is there is no meteoric material in the bays. So there is no shocked quartz, there is no microdiamonds. And therefore they cannot be impact craters. But of course these are not standard meteorite craters. They are not rock meteorites or metal meteorites, and they're not coming in at orbital velocities. These are soft touchdowns from slush balls going at much slower speeds. And so, no, of course they won't make shocked quartz or microdiamonds. It's not the same sort of impact. And therefore, the lack of meteoric materials, debris from meteorites, is not, does not disprove the impact theory for the Carolina Bays. But in terms of anomalous items found in the bays, this one I thought was rather interesting. This was a piece of wood found by Professor Richard Firestone, and he narrates this in his second paper on the Carolina Bays called The Case for the Younger Dryas Extraterrestrial Impact Event. And this particular sample is a piece of wood. You can see it's wood on the bottom, but the surface of the wood has been melted. And that's interesting because you need an awful lot of heat before you can melt wood. I mean, this is not charcoal, this is not carbon, this is, well, sorry, it is carbon, but it's not charcoal, it's not burnt, it's melted. And I've discussed this on the web with various people, with geologists and others, who have said, well, so what? You know, you found a piece of burnt wood, you know, there was a forest fire. Big deal. Well, actually it is a big deal because this is not a piece of burnt wood, this is a piece of melted wood. And that's a very big difference. And if we look at the phase diagram for carbon, this is the phase diagram for carbon. This is a graph of the transitions between the various states within carbon, so from solid to liquid to gas. And if you look at the bottom, somewhere near the bottom where it says graphite, and it'll say graphite all along the bottom there until it comes to vapor or liquid. Well, we're sort of interested in the sort of liquid phase, the change between graphite, or a piece of wood basically, and its liquid form. So we're looking at the transition between the grey section and the sort of purple section, the bluey purple section. And if you drop a line down from that join, it'll hit about, oh, I don't know, 4,500 degrees Kelvin. 4,500 Kelvin. That's about 4,200 degrees centigrade. Now that's an enormous temperature. It's the sort of temperature you would only get from the radiant heat from meteors entering the atmosphere. You wouldn't get that sort of temperature from a forest fire, that's for sure. And again, if we look again at the sample of wood, this is flash heating because it's melted on one side, but we can still see elements of wood on the other side of this small sample. So this is an instantaneous flash heating of this particular piece of wood. That's very difficult to explain in any other fashion other than the radiant heat from a re-entry vehicle. And we'll look at those sort of heats again in a minute. Another problem leveled at the impact theory is that the bays change shape as you go around America. So they start with elliptical bays along the northeast coast, and then as we go further south towards Texas, we end up with more circular, sort of heart-shaped Carolina bays. This is explainable, as we saw again from that diagram that we saw earlier about the different trajectories of these Carolina bays. The more northern bays are much closer to the primary impact on the Great Lakes, and therefore they might have a more shallow trajectory for their projectiles and therefore a more elliptical shape. The more southern Carolina bays are much further away from the Great Lakes, and therefore the projectile will have had a very different trajectory on its way down towards Texas. Perhaps a steeper trajectory, more like a sort of suborbital lob rather than the direct travel to the closer states up in the northeast. And therefore it will have a more circular crater when it hits the ground. So again, more work to do on that, but that's not really a problem with the impact theory. That is explainable by the impact theory. So all in all, I think the Carolina Bay impact theory, the secondary impact theory, has a lot going for it. So this is not the meteor shower theory, which I think has a lot of problems associated with it. This is the secondary impact theory of secondary slush balls being thrown across North America from the Laurentide ice sheet near the Great Lakes region. But if this did happen, if there was a primary impact on the Laurentide ice sheet, when did this happen? What we need to look for here is a devastation event within North America especially. Northern Hemisphere in general, but North America in particular. Because if this impact theory is correct, there must have been great devastation across North America for three main reasons. And the first of those reasons is the radiant heat of the inbound projectiles. These would have been like intercontinental missiles. They've only come from the Great Lakes, not very far away. So they would go out of the atmosphere and straight back into the atmosphere again in a sort of suborbital lob. So they'll be coming in at sort of space shuttle speeds. And the space shuttle, as it comes in, well, higher up it comes in at sort of Mach 25. But lower down as it starts entering the atmosphere, it's going at Mach 7 in the lower atmosphere. And that has a stagnation temperature of 4,000 degrees centigrade at Mach 7. Stagnation air temperature. Well, if you think about it, the air coming up to hit the space shuttle as it comes in on its final approach, that air is having to be stopped relative to the space shuttle. It's doing Mach 7 and it's being stopped relative to the space shuttle in almost an instant. And the stopping of that high velocity air, each molecule of air hitting the space shuttle, gives a high temperature, as we know, on any re-entry vehicle. And that stagnation temperature is 4,000 degrees centigrade at Mach 7. So if you're standing under the space shuttle as it comes in, you will feel its radiant heat. And you might say, okay, I'm not going to feel anything from the space shuttle coming in above me. But now think of 1 million space shuttles coming in above you and the radiant heat from 1 million slush ball projectiles coming in above you. Now you will feel a great deal of radiant heat that's not going to last very long. I mean, the re-entry is only going to be 2 or 3 minutes at the most. So you're going to have a flash radiant heat coming down from above from all of these projectiles that will warm and bake the ground below. That's going to cause devastation across North America. But even more than that, when these slush balls impact on the ground, there will be complete devastation. If we look at another of these LiDAR images, you can see there are bay formations all over this particular image. The entire ground would have been utterly devastated of all of its plant life, all of its animal life would have been devastated and destroyed. There would be nothing left alive down below. And this would cause an extinction event. It's bound to cause an extinction event within North America. So we need to find an era when we have an extinction event. But more than that, there would be a long-term extinction as well, because just imagine all of these slush balls traveling through the atmosphere down towards as far as Texas or further. There would be all of that ice in the atmosphere. Not all of it would re-enter. And of course, they would be very hot, these slush balls, as they're re-entering. So they would be gassing off ice and water vapor. And this ice and water vapor would stay in the atmosphere. Millions of tons of this ice and water vapor staying in the upper atmosphere, in the stratosphere, blocking off the sunlight and completely altering the climate for a significantly long period of time. And that's something that some people have mentioned. They've said that slush balls can't get up to 4,000 degrees centigrade. And so your theory is completely wrong. Well, sorry, but they can. Because the slush ball itself does not get to 4,000 degrees centigrade. Remember, if you have a re-entry vehicle coming in, the air that's coming up to the re-entry vehicle does not hit the re-entry vehicle. There is a shock wave in front of it, and the air is actually hitting the shock wave in front of the projectile. And it's that shock wave that's going up to 4,000 degrees centigrade. So, yes, the leading edge of this slush ball will be heating up from this shock wave, and it will be gassing off thousands of tons of liquid and ice into the atmosphere. But ice has a very high latent heat of melting and a very, very high latent heat of evaporation, or vaporization, you might call it. And so a lot of this slush ball would survive, even if the leading edge was heating up and gassing off. Remember, this re-entry is only 3 or 4 minutes. It doesn't take very long to come into the atmosphere. And so not all of this slush ball is going to gas off. A lot of it is going to be left to hit the ground, to cause all that devastation on the ground. But a lot of it is going to gas off as well and stay in the upper stratosphere as water vapor, as ice crystals, and have a profound effect on the climate for hundreds of years. And, you know, people talk about, scientists today, they talk about climate devastation caused by an insignificant amount of CO2 in the atmosphere. But this was real climate devastation. Millions of tons of ice crystals left up in the stratosphere, reflecting away the sunlight, causing global cooling for hundreds, perhaps thousands of years. So what we're looking for here is a devastation event and a sudden climatic cooling event in the fairly recent past, because these Carolina bays are relatively fragile. They're only made of sands and silts in a low bay rim that's only 2, 3, 4, 5 meters deep. It's a very fragile structure in the environment, and I don't think myself they could last for more than a few tens of thousand years at most. And so we're looking for a climatic and a devastation event within, let's call it, the last 120,000 years. Is there such an event? Yes, there is. We call it the Younger Dryas. And here is a graph of the Younger Dryas cooling. It was an unexpected cooling event 13,000 years ago, which lasted for 1,000 years. And it was very unexpected as well, because we were just coming out of the last ice age. So the last ice age started 120,000 years ago, and the world got cooler and cooler for over 100,000 years. And then suddenly it started warming into an interglacial. And the reason for that interglacial, we'll go through that in a later talk, because I've written a science paper, a peer-reviewed science paper, on the Ice Age cycle. And I've demonstrated why the world transitions from the Ice Age into an interglacial. But even without that, we know how these ice ages work, because there have been 8 major ice ages over the last million years. And each of them has operated in a very, very similar fashion. So you get this cooling for a number of thousand years, and then this sudden warming into the interglacial, which takes place in only 5,000 years, which is a very short time, geologically speaking. And so we were in one of these interglacials. We were going very surely into an interglacial. Some, let's call it, say, 15,000, 16,000 years ago. We were going into an interglacial. And then suddenly, as this interglacial progressed, the temperature cooled and we went into the Younger Dryas cool period. And here is, of course, that Younger Dryas cool period. It was a very sudden, very deep cold period, which took us back into the Ice Age for 1,000 years. But why did that happen? There must have been some very dramatic, very sudden event that took the Earth back into a ice age again, which no other ice age had done, and there was no explanation for it. And from my theory in my science paper that I wrote a couple of years ago, there is no reason within that paper why we should go back into a cold period. But we did. And here is that cold period. This is Professor Vance Haynes looking at deposits in this section. And you can see the black line across the center. That is the Younger Dryas. That is the cool period. And it's black because it has a lot of mosses and ferns. It has a different environment, a much cooler, slightly damper environment during that era than either side. And that is the Younger Dryas. So we know quite a lot about this cool period. This black line, by the way, is called the black mats, if you want to look it up. It's a very interesting transition point because, yeah, it's worth pointing that out. This is not just a cooling period, it's a transition period as well between one era and a completely different era above. So if you look at this, these strata, in the strata below that black line, we have megafauna. And I think they define megafauna as any animal that is over 30 kilos. That's known as megafauna. So below this black line, below the Younger Dryas, we find megafauna. Above it, there are none. They've just disappeared. So you can see that this is a transition line. And again with Clovis man, below this black line, you will find evidence of Clovis man, who was, Clovis man was the original Americans from thousands of years ago. And these, Clovis man has a great number of similarities with Sultrian man in France. And there is a theory that the Sultrians came across the ice sheet like Eskimos, sailing, on kayaks, following the line of the ice until they suddenly arrived in North America. and that is where Clovis man came from. It's quite an interesting theory, that, because their spear points are identical in France and Spain and for Clovis man in America. But that's a by the by. The main point here is that there is Clovis man evidence below the black line and none above. Clovis man simply disappears. So this black line, this Younger Dryas, represents a complete transition between Megafauna and Clovis man below and nothing above. They all died out. So this was an extinction event. This line represents a line of extinction 13,000 years ago during the Younger Dryas. And of course, the Younger Dryas is difficult to explain in any other fashion than some sort of meteorite impact. And Professor Vance Haynes goes further than this, much further than a scientist would normally go. And he says of the Younger Dryas period, the megafaunal extinction and the Clovis man extinction appears to have occurred in less than 100 years, perhaps much less. This implies that the extinction of the megafauna was geologically instantaneous and essentially catastrophic. So here we have a strata of catastrophe, an extinction event that happened in the recent past, 13,000 years ago. And as I've just said, it would be very difficult to explain that extinction event in any other fashion than some sort of meteoric impact for it to have happened so quickly. And so one thing that would explain this sudden extinction is an enormous great shower of 5 million secondary projectiles, slush balls, splashing down all over North America and leaving millions of tons of ice and water vapor in the atmosphere. Now that would cause a very sudden extinction event. Now, geologists will not accept this impact theory, but I think the impact theory for the creation and formation of these Carolina bays has a lot of merit. So I hope you've enjoyed this illumination talk, and I hope you can join us again next time. Thank you.